Greetings, aspiring scientists. Welcome to my video today on IB Chemistry, Paper 1A, Practice and Advice. My previous Paper 1B video did pretty well, and so I decided to make another one for Paper 1A. I think nobody really asked for this. You know, my Paper 1B video, I saw a lot of posts on social media saying like, I don't know how to do this, please give me some advice. This is not the case for Paper 1A. People are generally pretty okay with multiple choice Paper 1A, but I will say that a lot of people, including my students at my school, get much lower grades than they expected on Paper 1A, so there's a lot to learn about how to do it. So I will be going through a whole similar to an IB paper, very similar to in this video just after I give some general advice. And I'll be indicating which questions are SL or HL, so this can be used for both SL or HL. All right, so some general multiple choice test advice. This is just randomly I got from my mind, from Google, from AI, so you could find this on your own, but I'll just go through some points that I agree with. Read the question extremely carefully. Underline words that are critical for the answer. Okay, so I'm talking about critical nouns, adjectives, adverbs, those kind of things that really affect whether an answer is correct or not. Read it twice, 3 times if you need. Next, be cautious of absolute words such as always, never, all, etc. These are sometimes the answer, but more frequently they are traps. There's a lot of cases where there's exceptions or things that are not so clear, not so well understood, and we wouldn't say absolute words like this. So just keep that in mind, especially if you have to guess. 3, consider longer phrased answers as possible correct answers. Detailed explanations with a lot of correct key points are frequently expressed as the correct answer. Again, be careful with this, but I think this is generally true. All of these are just going to be probability based, these advice points. So if you see an answer that's like explaining things very clearly with 2 or 3 points and the phrase is a bit longer than the other answers, consider if that might be the right answer. 4th, skip questions you'll struggle with to do later, but always submit an answer for every question, okay? Make sure you fill in the bubble, fill in the answer for every question on the test. You have at least a 25% chance of getting a point if you just try on Paper 1A. 5th, use the process of elimination to eliminate incorrect answers and increase your odds if guessing is needed. So even if you really don't know, you can't find the correct answer, you might be able to eliminate 1 or 2 of the other answers just because they make no sense at all. It's a very good skill. And when you're going quickly, just start by eliminating the ones you know that are not correct and cross them out on the paper, and that leaves you thinking about only the ones that remain. But if you have extra time at the end, go back and see if you really eliminated the correct things or not. Always consider every option. That brings me to number 6. So seriously consider all options for an adequate amount of time, okay? Don't immediately eliminate something that looks wrong without correctly giving it some time. Time is a valuable resource on IB exams, of course. So you have to find your sweet spot of what gets you the most points when you do past papers. 7, draw pictures when able, especially like Lewis diagrams, graphs, and do full math calculations when necessary. So you'll probably be able to recognize a question that requires a math equation when you see it. You'll get some variables, perhaps some equations, some references to the data book. Don't just guess on those, actually do the calculation. Or try them anyway. 8, when 2 answers appear to have the exact same result or meaning, it's likely that neither is correct. I think this is actually one of the best, most insightful points on this list. there can't be two correct answers on a paper 1A test, right? So if you get two answers that essentially mean the same thing, end up with the same kind of resulting point, then it's likely that neither of those is correct because there can only be one correct answer. And then ninth, when three answers are similar and one is not, the different one is frequently incorrect. You'll see this sometimes. There's three kind of similar answers where they're going to try to really make you distinguish what is correct between those. And then a fourth one that's just totally opposite or different. Usually not that, although sometimes it is. So again, this is a probability thing. 10th, use information between questions to help you solve them. Diagrams, equations, or definitions from one question can help you remember or give clues to another. This is important. If you're stuck on one question, skip it, move on. You might suddenly come across something that gives you a hint later on, or you might be doing a question later on and realize that something you did earlier was incorrect because of something that you've seen in a future question. Okay. One more thing I want to add, I think, is that if an answer seems vague or that it could be the right answer in some situations, it's usually not the answer, okay? Think about the perspective of the author of the test and the people grading it. They don't want to have claims and problems with parents or students later on or teachers who say, you know, this answer was unclear. Why is this correct or not? You know, if they give an answer, it's going to be most likely very clearly correct. So if it's vague or something, probably not. All right, and then I just want to categorize some levels of paper 1A understanding based on my experience. This is one way you might consider where you're at. So if we think about a level 1 understanding, this will generally get IB scores 1 to 3. So someone here can usually or sometimes identify the filler answer that makes no sense at all among the options. Not every question has one of these, but a lot of them do. I'll show you how to identify them today. But this leaves you guessing with a 33 to 50% chance instead of a 25% chance. And if you ever end up choosing a filler answer like one of the ones I'll show you in this test, you seriously need to go back and study that topic basically from the beginning, because those answers really don't make any sense. Level 2 understanding then is like an IB 4 to 6, 4 to 5 maybe. You can identify and avoid filler answers quite often, and you're fairly quick and efficient at identifying what you think is the right answer using some actual knowledge and methods. And you can do that consistently and efficiently and actually finish the test. You do draw diagrams and use math equations to find answers when necessary. Unfortunately, you fall for the well-concealed traps sometimes, and there's almost always some traps in the paper 1A options. So to really get to that level 3 at the bottom, IB score 7, you have the above skills, but you also put yourself in the mind of the exam authors. You understand who they're trying to trap, and you avoid being that person. You understand every answer and why they're on this exam, not just the correct answer. You understand what all the other options mean and when they would be correct, but they don't match this particular question that's being asked, okay? And if this person misses any marks, it's due to one or two topics they couldn't master, or they ran out of time due to comprehensive answer checking. So we want to try to get to a 7 and try to get as quick and efficient at it as possible. So I'm going to go deep on every question and try to talk about every possible answer and what they mean. You don't have time to do this on a real exam. You have time to do it on your practice, though, and past paper practice that you're doing. On a real exam, though, you have to go fast. So let's get started. Start with SL. Question 1. Which type of material is a good conductor of heat and electricity in solid and liquid states, is insoluble in water, and typically has a high melting point? Okay, so one of the first things you want to do, I would recommend, is remember where in the syllabus this question is coming from. So I think it's coming from the bonding to materials section, where you're trying to link bonding types to the materials and properties they have. So it's after covalent, ionic, and metallic bonding. Which of these is a good conductor of heat? Insoluble liquid, insoluble in water, typically has high melting point. So we underline good conductor of heat and electricity in solid and liquid states. Insoluble in water typically has high melting point. So that doesn't mean always. So we want to go through these, and you basically just want to take these options, covalent, molecular, metallic, covalent network, and ionic, and apply them to these three conditions that are required by the question. So covalent, molecular, how does this fit in? Is it a good conductor? No. In the solid and liquid states, unless it's a charged polyatomic ion or something, but we're not going to consider that too much. What about insoluble in water? Well, that depends on its polarity, right? Typically has a high melting point. That really depends as well, but more often than not, it's lower. So, does that look like the correct answer? No. We have a definitely not, and then kind of vague, leaning towards not. Metallic bonding then. Good conductor of heat and electricity in solid and liquid states. I was going to say yes, but we'll just say good. It is. Insoluble in water. Yes. Pure metals don't really dissolve in water. And typically has a high melting point. That is also yes. If we're talking about most of the metals, transition metals, some of the alkali metals and such are lower, but generally we can say this. So this looks like a very good contender for this answer, and it probably is. Covalent network. Let's consider this. Good conductor of heat and electricity. Generally, they are pretty bad unless they have delocalized electrons. But generally, we'll go with bad here. Insoluble in water. Yes, that is true. Typically has high melting point. Yes, that is true. But because of that first one, I'm going to be skeptical of this. Another point about this is that covalent networks cannot be liquid, though. If it ever becomes a liquid, the network is destroyed and it won't be classified that way anymore. So for that reason, I really think it fails the first property here. Ionic, good conductor of heat and electricity in the solid and liquid states. Liquid, yes. Solid, no. So that's going to be why this answer fails. Usually it's soluble in water, so that doesn't work there. It does usually have a high melting point, though. So looking at this, I think it's pretty clear the answer will be B, metallic. Again, we don't want vague answers like A that could be debatable. All right, number 2. What is the volume in decimeters cubed of ethane gas, C2H6, produced when 0.25 decimeters cubed of ethine, C2H2, reacts with 0.4 decimeters cubed of hydrogen gas, H2? All volumes are measured under the same conditions. We get this equation. So where does this come from? This is going to be mostly a stoichiometry limiting reagent type of question. So remember everything that's required to answer those types. So it looks like you're just going to basically have a math equation going on, right? You've got 0.25 of this. Remember that Avogadro's law says we can use volumes as kind of mole ratios. So if we have 0.4 of this, well, what's going to be limiting here? 1-to-2 ratio between C2H2 and 2H2. That means double of the C2H2 is required. Do we have that? No. We have less. We have only 0.40 of H2, so this is limiting. That means we're going to use that to find out everything else. Then what's the ratio between H2 and C2H6? 2-to-1, so we can take 1/2 to find this. That comes out to 0.2. That's what I think the answer will be here. But I still want to understand what mistakes would lead you to the other options. That's like a highest possible level understanding of all the answers here. So B, if C2H2 was limiting, I think you will get the answer 0.25. If you ignore the coefficients in the balanced chemical equations and ignore the ratios and just assume that they're all 1, I think you'll get this C answer. So don't make that mistake. And then A, I think, is kind of the filler answer. This makes no sense to me. How can you have portions of gas combine into one portion of gas and have that volume be higher than either of the first ones? If they're behaving ideally, A is completely impossible. And if you understand anything about ideal gases, I don't think you should say that. All right. Question 3, how many pi or sigma bonds are there? But they're in but2-ene nitrile. So HL question. So we need to be counting the sigma and pi bonds. What I'm going to recommend that you do is add the hydrogens onto this so that you don't forget them. This is the skeletal kind of organic structure. But don't forget, carbon needs 4 bonds, and anywhere it doesn't have it, there are hydrogens. Okay, and then I'm going to draw with maybe red. I'll indicate with a single slash the sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this one is the central one usually. All right, so right away, you can basically say B if you're going quick, but let's identify the pi bonds as well. I'll use maybe blue, purple. So there is 1 in that double bond and 2 in this triple bond. So 3 and 9, that solidifies. Absolutely the answer is B. Why would you select the other ones though? If you forget the hydrogens as sigma bonds, I think you would select A. What else? These ones, I don't really know how you get those sigma bonds, but the pi bond's 5. That's if you count every bond in the double triple as pi. You will get 5, but that's not the way to do it. A double bond contains 1 sigma 1 pi, triple contains 1 sigma 2 pi. Okay. What are the main products when concentrated NaCl is electrolyzed using inert electrodes? HL, this is Electrochem. So we just get choices of anodes and cathodes. So definitely underline this is concentrated. That really affects the answer. And we're using inert electrodes. So basically go through these, but remember, red cat. That's how I usually remember. Reduction always happens at the cathode. Okay, so you need to consider what reactions are going to be happening at the cathode versus anode. So we can have either water or chloride getting oxidized at the anode. In concentrated NaCl, it is chlorine. Chlorine oxidized at anode when concentrated. Even though the electrochemical potentials, if you use that method, will tell you that it should be water, due to the high concentration and the over voltage going on, chlorine gets oxidized instead in concentrated. I think there'll be some percentage, like 75 to 25 or 90 to 10 or whatever, depending on the concentration. But this means that the anode must be oxidizing Cl minus to produce Cl2 gas. All right, and then what happens at the other side? Reduction. Well, if you compare sodium with water, those are, I guess, the two possibilities for what is reduced. Sodium is pretty much never reduced. That's one thing you should learn about this topic. So look for the reduction of water. And I think you'll find it's this equation, H2O plus electron goes to 1/2 H2 plus OH minus. That's in the data book in the electrochemical potentials page. And so that's going to be producing H2 gas if that happens at the cathode. That leaves us with only one answer, which is A. Cl2 at the anode, H2 at the cathode from the reduction of water. Let's consider the other options though. If water is instead oxidized instead of Cl2, mainly we'll be producing oxygen O2 gas. That happens in dilute. So if you miss that concentrated word or you didn't study it, you make that mistake. Then C, let's look at D first actually. H2 and Cl2, this is the opposite of what we said. So if you mix up the electrode locations or what they do, you would answer D. So if you forget red cat, for example, if you think reduction happens at the anode, you'll probably get this. And then this is a combination. C is a combination. If it was dilute, and wrong electrode. You get double wrong answer. So definitely don't do that. A is the answer here. All right, number 5. HL. The reaction between bromine and nitrogen 2 oxide follows a two-step mechanism. Br2 plus NO in equilibrium with NOBr2, fast. Then NOBr2 plus NO goes to 2NOBr, slow. What is the rate equation? So we mainly want to look at step 2. Slow steps are rate determining steps. And each step tells you a collision between the reactants in these elementary rate steps. So we have a collision between NOBr2 and NO, one of each. So this is second order overall, first order with respect to each. We will have some constant K, and the rate is equal to that. Okay, so this is correct. However, you'll notice that is not an option in A, B, C, or D. So we need an alternate expression for something equal to this. Now, this used to be common on exams, but I don't think this type of problem appears so much anymore. In fact, I thought it wouldn't, but this exam I was looking at proves me wrong. This was on a real exam. So we need an alternate expression for this, and so we kind of need to know that the NOBr2 concentration is essentially proportional or related to Br2 colliding with NO. So even though that reaction is fast, it still depends on the initial concentrations of Br2 and NO. And that means with a different rate constant, we can say that this is equal to rate equals K times Br2 times NO, replacing NOBr2 times NO. And essentially, NO is second order then, it goes squared. And that is an option here. That's option D. So why would you select the other answers? What traps are there? This B is just the step 1 rate, the fast rate. It's not rate determining step. What else? C, I think this is just the filler, makes no sense. How could you have the final product affecting the rate at getting to the final product, especially if it's not in any of the other sections? It doesn't make any sense. A then, I think if you just look at products and the stoichiometric coefficient, NOBr is the final product, right? And it has 2 NOBr in the final step. If you somehow just think that that's squared, then you would say that. But that's totally not how to do rates. So this is kind of a filler as well. Answer is D then. And of course, this is rates, I forgot to mention. Number 6, volume of ethyne as it reacts with hydrogen is shown in the graph. C2H2 plus 2H2 goes to C2H6, which graph shows how the volume of hydrogen changes with time. All right, so this is again stoichiometry and a bit of rate graphs maybe. So we have volume versus time graphs. H2 and C2H2 are reactants. How are these graphs going to look? Well, the ratio of C2H2 to H2 is 1 to 2. That means H2 must be consumed twice as much, both over time and as a final amount. So looking at these, the one that fits that is B. If they both start nearly at the same volume, H2 will go down faster and finish lower. All right. A really doesn't make sense if products are being produced and C2H2 is decreasing. This also must decrease over time. C, if there was inverted coefficients, so if it was 2C to H2 plus H2, you would expect this graph. Where twice as much or more C2H2 is consumed. And then D also makes absolutely no sense. How can H2 possibly increasing if it's being consumed in this system? So no. That's kind of the filler. Next, SL, what's the concentration of OH minus in mole per decimeter cubed in a solution at 298.15 K with pH of 4.5? So we get some pH equations, that's nice. I label this as SL, but SL, you don't need to know about POH, I think. But you can still do this question. So there's actually two methods to do this question, right? You can either use KW or you can use pH-POH relationships. So if we do POH, this is kind of maybe the HL quick method. So POH equals 14 minus pH, which is 14 minus 4.5, which is 9.5, and then 10 to the 9.5, minus 9.5 is equal to 3.16 times 10 to the minus 10, which is your answer. Okay, that's maybe HL, but HL students can, of course, use the SL version with KW. You still need to know this. So KW is equal to concentration of OH minus times concentration of H plus. So to get concentration of H plus, we can take 10 to the minus pH, 10 to the minus 4.5, so that's 3.16 times 10 to the minus 5. And then OH minus concentration is equal to KW over H plus, which is In the data book, constant section 1.00 times 10 to the minus 14 divided by 3.16 times 10 to the minus 5. And we get 3.16 times 10 to the minus 10. Again, the correct answer. Okay, so what are the other options? We do have, of course, the H plus concentration as an option if you fall short of the bottom method and only go halfway. So don't fall for that. I don't know what would lead you to A and B, but some math error, maybe forgetting zero somewhere, will lead you to A. And option B is the H plus version of A, so of some math error, if you didn't go all the way there. So C must be the answer. This is, of course, acids and bases. All right, next. Which element is a P block metal? This will be periodicity and trends. SL question. Pretty tough though. So you definitely want to be looking at your periodic table in the data book, and specifically right around the P and D sections. That's where these metals, metalloids are going to be. Specifically, you want to look at the section that has boron, aluminum, silicon, phosphorus, gallium, germanium, arsenic, selenium, tin, antimony, tellurium, bismuth, polonium, and astatine. Roughly this section. Why? This is the metalloid staircase, okay? So you should definitely know where the blocks are on the periodic table, P, D, S, F, and so on. But there's another section that is really important to know, which is the metalloid staircase. And I think you have to memorize this. So this line right here, in between boron and aluminum, very important line on the periodic table, because this is where the metalloid staircase starts. You go over to the right one, down one, over one, down one, over one, down one, over one, down one. Okay, this is the metalloid staircase. Most things that touch this are either classified as metalloids or contain many of the properties of metalloids. Okay, so for example, A, astatine, metalloid. It's touching that staircase on the left of its box. Cadmium, that's just far in the D block, so it's just clearly not part of the P block. It's a transition metal. Tellurium is also touching this staircase. It is a metalloid. Tin. Tin is touching in the top right corner, but we're talking about sides making contact with the staircase to be classified as a metalloid generally. So this is in fact a metal and still in the P block. It's not in the D block. So D answer. There are some exceptions to this, especially near the top. Like I think aluminum is classified clearly as a metal and not a metalloid. But especially as you start going down, things that touch this staircase have metalloid properties. Okay, good. Number 9, SL, a fixed volume of an ideal gas, initially at 30 C and a pressure of P, was heated to 60 C. What's the resulting pressure in pascals? So this is a gas laws question, SL. So I think what you need to use is PV equals nRT. Pressure is directly proportional to temperature. So if this is heated up, the pressure must increase. But this is Celsius, right? We need Kelvin. So 30 to 60 is double numbers, but it's not double the absolute number. So 273 plus 30 is like 303. And then this is like 333. So it's just a slight increase in temperature. That means there should be slight increase in pressure, right? So that's a little more than P. So B, a little less, would be the inverse if you thought that pressure is proportional to 1 over T. But you shouldn't think that. You have the ideal gas law equation in your data book, PV equals nRT, so P proportional to T. 2 times P for D here. This is if you forget to convert to Kelvin. So don't do that. Half of P. This is if you take the inverse relationship and forget Kelvin. So double mistake there, don't choose that. Okay, good. Number 10, what are the oxidizing and reducing agents in this reaction? SL, this is Electrochem redox. So what you want to do in this type of question, just label the oxidation state of every single atom in every single atom or molecule. Okay, so ClO minus plus 1 for chlorine here, quite rare, but oxygen is more electronegative, so oxygen going minus 2 in this is the only way to make this whole thing minus 1. SO2, sulfur in this is plus 4, oxygen in this is minus 2, balances out to 0. H2O, hydrogen is plus 1, oxygen is minus 2, balances out to 0. Cl minus is minus 1, obviously. SO4, 2 minus, you'll find sulfur in this is plus 6. And oxygen is minus 2. It's the only way to get overall charge of minus 2. And then H plus is obviously plus 1. Okay, if you forget how to do this, I'll just show you quickly for sulfate. So there's some rules for finding oxidation states, right? One of them is that oxygen is almost always minus 2. So if we have 4 oxygens at minus 2, we want to find what sulfur is. They equal the total oxidation state on the complex. So that equals the total charge of minus 2 in the top. So just solve that for S. S must be plus 6. You can do that for most of the atoms if you know the rules. One of the rules, though, is that halogens are usually minus 1 unless they're combined with a more electronegative negative element, which is ClO minus, breaking that rule. That's why this is kind of a tough question. So, what gets oxidized and what gets reduced? Sulfur goes from +4 to +6. That is an oxidation. And chlorine goes from +1 to -1. That is reduction. Everything else stays the same. So oxygen and hydrogen are not doing redox in this. But the question is the agents, right? What causes oxidation? In this case, it is the ClO minus. And what causes the reduction? It is the sulfur dioxide, SO2. So that is C. ClO minus causes the oxidation, it's the oxidizing agent. And SO2 causes the reducing agent. All right, and why would you choose the other options? Well, you might choose option A because H2O to H plus looks kind of like H goes from nothing to +1, right? But you have to understand in oxidation state terms, that's not correct. H is still +1, even in H2O. Okay, what about B? If you mix up agent versus ED, like oxidized or reduced, the agent is the opposite of that, right? So you would choose the reverse language. That would be B. Don't do that though. And then D, I don't really know, but this S was +4 going to +6. So maybe if you think that is oxidation, then you choose this is SO2 oxidizing, but that's not how it works. This is kind of the filler in my eyes. If you understand reduction, oxidation, labeling at all, you would not label that. All right. Next, number 11, which products may form when propane undergoes incomplete combustion? SL. So this will be from the fuel section of the syllabus. And this is really a knowledge thing, I think, incomplete combustion. So we can either have fuel plus limiting O2 goes to CO and H2O, or very limited oxygen goes to C and H2O. So a couple things you'll notice. H2 is never produced by incomplete combustion or any type of combustion that I know of. So that immediately eliminates A, C, and D and gives you the answer B. B does have two of the options I wrote here, CO and C. It also has CO2 though. But you need to understand that incomplete combustion will never be 100% of any of these reactions, even the regular combustion. Fuel plus O2 goes to H2O and CO2. These things all just have some percent depending on the amount of available oxygen. But they will all occur to some degree because some pockets of air have a bunch of oxygen, some have almost none. Depending on where you are in the reaction mixture, it's just down to chance. So even in incomplete combustion, in a situation that's real, you'll have some CO2 produced, but also CO and C. H2 never is produced in combustion of any kind. What is the reason for that? It's because H2O is the most stable of anything here, right? It's more stable than CO, C, and CO2. And so when it comes down to it, it's more energetically stable to form that H2O first with any oxygen available. Okay. Number 12. SL, 2 moles of NO, 1 mole of Cl2 were mixed together, and the system was allowed to reach equilibrium. Get this data. Which relationship is correct for this equilibrium at 35C? And we have a K at 35. Well, this is equilibrium, obviously. Topic. What I'd recommend is that you draw the K expression for this. Products, concentration on the top, raised to their coefficient as a power. Reactants on the bottom, coefficient as a power, multiplied by the other reactant to its power of 1. So our K is, in fact, much greater than 1. What does that tell you? That tells you that at equilibrium, this system was allowed to reach equilibrium. There will be much, much more products than reactants. This reaction is favorable towards products. And that means NOCl will have much greater concentration than the reactants. And NO is a reactant. That fits with C answer here. So why would you choose the other options? You can consider that. You might just say that 2 NOCl means that there should be double the amount of Cl2 for the concentration of NOCl. What about B? This is the opposite relationship for K. So if you somehow put the reactants on the top, or if you thought that a high K means more reactants, you would probably say B, but don't do that. And if you just say in the K expression, both are squared, equal power, so maybe the concentration should be equal, but that's not true. Don't do that. The answer is C based on the reasons above. All right, good. 13, what's the theoretical yield in grams of ethanamide that can be produced from the reaction of 4 grams of ammonium carbonate with excess ethanoic acid? 2 equations that are kind of linked together through CH3COONH4, and then some molar masses. So this is stoichiometry. And have to do some math. Look at the ratios. In the first equation, 2 to 1 to 2 to 1 to 1. And then everything's 1 to 1 in the second equation. So I'd recommend you find the moles of NH4 to CO3. that's equal to mass over molar mass. So 4 grams divided by 96.11 gram per mole. That gives you 0.0416. We have a 2-to-1 ratio. So 0.0832. Of CH3COONH4 can be made. Then we have a 1-to-1 ratio in equation 2. So 0.0832 mole of CH3CONH2. And then we finally need the mass of that. So that's moles times molar mass, which is given in the question, 59.08. That will come out to 4.92, sorry. Which is our answer here, A. Why would you choose the other options? If you forget a 1-to-2 ratio, you'll end up with D. If you apply a reverse 1-to-2 ratio and go half instead, you would get C. So don't do that. And B, I think if you somehow include H2O, in the final mass, or I guess if you just use the left side of equation 2, you end up with B, but that's definitely not correct. So A answer there. And I also want to say, you have to realize that this question said with excess ethanoic acid, that means you don't need to consider limiting reagents. You know that your ammonium carbonate is limiting. All right, good. 14, what's the sum of coefficients when 1 mole of propan 1-ol, C3H7OH, undergoes complete combustion? So you basically just want to fill this out. This says 1 mole, so you immediately need a 1 here. And then just balance the rest. So we will need 3 CO2. And then how much H2O? 4. We've got to deal with 8 hydrogens. And then how many O2? We're going to need 4.5, 4.5. So 1 plus 4.5 plus 3 plus 4. That should lead us to 12.5, which is answer A. Why would you answer the others? So if you forget, which people often do, the hydrogen on the very end, you will get this answer B, I think. If you forget the oxygen in that, as needing to be balanced, I think you will get answer D. And if you forget both or some combination of forgetting things, I think you will get C. Okay. So this topic was stoichiometry and a bit of fuels. It often shows up, this combustion. Good. Number 15. Which two elements form a compound with the strongest attraction? Strongest ionic attraction. So immediately this is ionic bonding. Maybe a bit of materials, bonding to materials properties. So what you should not do is check the electronegativity difference between these, I think. What affects ionic bonding strength is ionic charge and radius. Remember that we've got electrostatic force is proportional to Q1, Q2 over R squared. So smaller radius R will create greater forces of attraction and stronger attraction here. And ionic charge is the Q in this, so if we increase the charge magnitude, we'll increase the force. Here though, all the charges I do believe are the same among all the answers. Lithium plus, K plus, lithium plus, K plus, selenium 2 minus, and O2 minus. When these become ions in ionic compounds, this will be the case. So we're basically just looking at radius. Now the radius of Se2 minus is greater than O2 minus. It's lower on the periodic table. And the radius for the cations, we've got potassium greater than lithium. Again, lower on the periodic table. So we need lower radius. That means we need oxygen and lithium. So that answer will be C. So why would you select the others? Well, the biggest electronegativity difference, if that's what you're going on, is between potassium and oxygen. Delta chi, I think it's written as electronegativity difference. Potassium and selenium have the largest radii, so if that's what you think will cause the strongest attraction, you would select that, but don't go for that. And lithium and selenium is just the last combination among these four elements that they've chosen, so they kind of had to put it here. It's kind of a filler, and it's just mixed in between the other options, but it's not the answer for the strongest attraction. All right, good. Next, HL. Consider two half cells, aluminum and aluminum 3 plus with nickel 2 plus. What will be the cell potential in volts when the two half cells are connected? And then we get the potential values here. So this is Electrochem. So you basically just need to remember an equation. E naught cell equals the right-hand electrode potential, which is usually reduction. Anyway, reduction has to come first, minus left-hand electrode, which is oxidation. And so, which of these will be reduced? Both of these that are given are reduction equations. The one that's more positive will be the one that happens spontaneously when just these two half cells are connected. So that will be nickel. It's more positive. So we start with minus 0.26. It's nickel minus aluminum, which is, again, you must use the reduction potential here, minus 1.66. And that gives you plus 1.40. That's my answer there, volts. So if you mix up the sign or the ordering of this, you will get C, right? There might be several reasons why you do the wrong order, but remember that E cell is the reduction minus the left-hand electrode where the oxidation is happening, but you use the reduction potential of that, which is what we're given here at the top. Now, A and D you can see are obviously related as well, just opposite signs. And I think what's going on here is that if you think that the E cell depends on the number of electrons transferred, or the number of times that this process happens, you know, we have, it's already written at the top here, I'll just use this. We have 3 electrons and 2 electrons, right? You're taught to eliminate electrons. That means you need to double this and to triple this to get your electrons to cancel out. And since we've said that nickel is reduced and aluminum is oxidized, we'll instead be basically doing this, right? Al3 plus 3E. So we're canceling out these electrons with these 3 electrons. You still need to double aluminum though to get 6 electrons. But if you think that this must be applied into this equation, and you end up doubling 1.66 and tripling 0.26, you will get answer A or D. And D is if you use multipliers and mix up the order. So don't be doing that. These potentials do not depend on the number of electrons transferred or the number of times that this process happens. They are set for the equation that's written there on the left. And one reason for that is that volt is equal to joules per coulomb, right? So whether you have 3 coulombs of electrons or 5 coulombs of electrons or 10, it's included in this joules per coulomb value. So it doesn't get affected when we up the process. Okay, good. HL, which statement about the standard hydrogen electrode, SHE, is correct? So this is again Electrochem. So we need to read these very carefully and find what's correct. standard hydrogen electrode has a standard reduction potential of 0 volts at any temperature. That looks to me to be good. B, any acid with a concentration of 1 mole per decimeter cubed would give the same cell potential. Not true. Weak acids have equilibrium. And that means if you use 1 mole per decimeter cubed of a weak acid, your H plus concentration will be less than 1. And the standard hydrogen electrode must have 1 mole per decimeter cubed concentration of H plus. C, the standard hydrogen electrode must be the anode when measuring E naught values of another half cell. Absolutely not true. If you know anything about the standard hydrogen electrode, you'll know that it's the 0 point, but many things exist above and many things exist below it on the electrical potential scale. So when things are above or below it, it will change whether it is the anode or the cathode. So it switches depending on what is attached. Okay, and then D, cell potential is unaffected by the pressure of the hydrogen gas. Not true. The hydrogen gas, as far as I know, must be standardized. I think it's 100 kilopascal. So concentration and pressure are kind of similar, right? A higher pressure is like a higher concentration, most things considered. So we need to standardize this for this potential to be standard. Temperature, though, the standard hydrogen electrode has a reduction potential of 0 at any temperature. It can be 0 Kelvin, or not 0 Kelvin, 0 C, 25 C, 50 C. The whole system of table of potentials around it will change depending on the temperature, but our definition of the standard hydrogen electrode is that it is the 0 point at any temperature. So this is really just, do you understand the definition and restrictions of what the standard hydrogen electrode must be? All right. Which statement about catalysts is correct? SL, this will be rates. Let's just go through each of these. We need it to be correct. Catalysts alter the mechanism of the reaction right away. Yeah, I know that's true. B, catalysts affect endothermic reactions more than exothermic reactions. No. If you draw your profiles, if we have an exothermic and our catalyst reduces that, well, every reaction essentially has an opposite. So the opposite of this, the reverse reaction of that, will also have its activation energy reduced by the catalyst exactly equally. So it's not more than the exothermic for endothermic. C, catalysts increase the kinetic energy of reacting particles. Absolutely not. Catalysts decrease activation energy only. And then D, catalysts increase rate and are used up in a reaction. All right, so this is a trick they like to do. Put something correct first and then something wrong next. And are used up in a reaction? No. Catalysts must be regenerated and reformed. So so they don't get consumed by definition. Okay, so that does leave us with A. Catalysts alter a mechanism. As I showed in one video I made recently, instead of this transition state, they'll give you a new one, maybe an intermediate, a second transition state there, right? This is a different mechanism. And the mechanism has a pretty strict definition, right? It's like how things collide and what intermediates are formed. All right, number 19, SL, which oxide is the most basic? So this, I think, is periodicity, acidic and basic oxides. So MgO, this is a metal oxide. Al2O3. This is a metal, kind of metalloid oxide. SiO2, this is a non-metal oxide. SO3, non-metal oxide. And I think B here is a case where you need to just know and memorize that because aluminum is close to being a metalloid, it's in between metals and non-metals. It is amphoteric, meaning it can act as a base or an acid depending on what is around it. But the pure metal oxide, MgO, metal oxides are basic. And so A is the answer. Non-metal oxides are acidic. So they are not the answer. Okay. And then number 20, SL. A crystal of copper 2 sulfate is in equilibrium with copper 2 sulfate solution in a stoppered flask at constant temperature. Which observation is possible? It is in equilibrium in a closed system, constant temperature. Which is possible? A, the shape of the crystal changes slowly over time. We'll consider that in a second. B, the color of the solution becomes darker. What does that mean? That means concentration of copper 2 plus, that causes the color, increasing. But we have an equilibrium here, right, between copper 2 plus and sulfate ions going to from the aqueous state to the solid state. In equilibrium, is it possible for copper 2 plus to be increasing or in fact changing at all? No. This is not possible. Definition of equilibrium says concentration of things involved is constant. C, the size of the crystal decreases. And this essentially means the moles of CuSO4 decreases, which is kind of the same thing as B. It's kind of a concentration of that solid, if you want to think about it that way. But this is not possible in equilibrium. It's because size is some proportional to amount, right? We have to assume that. D, the volume of the liquid decreases. Well, the liquid is water, and water is not part of this reaction at all. Stoppered flask means there shouldn't be any loss. No evaporation. And the ions that form the crystal essentially have no volume effect on the liquid. So, not this either. Okay. Answer is A. How is it possible that the shape of this crystal changes over time, though? Well, you could imagine if we have our crystal like, I don't know, this shape. Equilibrium says that whenever one solid particle leaves and becomes ions, another one comes in and bonds there, right, at some other location. So now the shape of this changes, but the overall size is the same, the amounts are the same. It's just because the reactions continue, the location is not set, and so the shape can change. All right, so I think I'm going to stop this video here. It's way over an hour. A real paper 1A HL is 40 questions though, so I'll make another follow-up video with the remaining 20 questions I have. It's just going to take me a while to edit this and get it out, which I'd like to do as soon as possible. So thank you for listening. See you in the next one. Bye-bye.